Welcome to the 13th Porous Media Tea Time Talks. With these seminars, we want to give junior researchers working on porous media the chance to present their work to the scientific community around the world. This is meant to be the complementary to geoscience and geoenergy webinar, which you can find in our featured channel. Just as a reminder, call for abstracts is still open for the Interport 2021, which will be held online because of the pandemic this year. I am Mohammed Nouraipour from University of Oslo, and I'm here with my co-organizers, Tom Boltgrace from Ghent University, Catherine Spurin from Imperial College London, and Nora Brando from Federal University of Oberlândia. With that, I would like to introduce our first speaker. Senyou An is a third-year PhD student at the University of Manchester from Group of Integrated Multi-Scale Porous Media Research. Senyou's work covers advanced computational and experimental methods for pore-scale multiphase flow, reactive transport, fluid-fluid interfaces, and non-classical theories of porous material to address fundamental problems in engineering and natural applications. Today, Senyou will introduce his work about the effect of pore-size correlation lengths on two-phase flow and transport properties. Senyou, thank you for participating in our studio, and the floor is yours.
Okay, thanks for the introduction. Hi, everyone. I'm Senyou An from the University of Manchester. Thanks to my colleagues Shahrul, Hamid, Masoud, and my supervisor Wahid for the collaboration of this work. Today, I will talk about the effect of pore-size correlation lengths on two-phase flow and transport properties. As a key application, the background of this research is low salinity water flooding to enhance oil recovery. We should revival low salinity water flooding at different scales. At the nano scale, it shows electrokinetic phenomena. From nano to macro scale, we can observe wettability alteration and viscoelastic effect. This is a work from Maheni to study the oil bubble detach from solid phase when around the fluid changes from high salinity water to low salinity water. We also did the simulation work to investigate the dynamic change of oil bubble. From micrometer to centimeter scale, the studied phenomena are usually transport mixing and so on. It's our work about solution transport in pore network. Go to larger scale, people usually studied the relative perm curl and transport phenomena. At macro scale, we experimentally studied the solution transport in the macro model and the 3D porous media. This work is from Nikos and Wahid. Using water displace oil to different saturation, and at specific saturation, the slot is injected from left inside. We can see that the slot quickly occupies the flowing zones, but for the stagnant regions, the diffusion dominates the transport is very slow. We also did the similar work in a 3D sample. It's the state of water saturation of around 0.85 and the Pecklin number 600 around. After inject slot, we choose one subdomain at different times, and we can see that the distribution of concentration at some area, the transport is very slow. Statistically, the resident concentration shows non-frequent performance. Each line represents a saturation. From the experiment, we can observe that stagnant region is key feature of non-frequent performance, especially for these low saturations. So we had one question: how the pore-size correlation lengths affect the distribution of stagnant region and the transport phenomena? It's not easy to design a physical model with specific correlation lengths. So we use the numerical pore network modeling method to address this question. The first step is to generate expected samples. We mapped the network topology and the correlated radius field to generate the correlated pore networks. Here we maintained that the size of pore body and pore throat have identical log normal distribution. The distribution of big pores and small pores are different for this one. is uncorrelated network with random distribution. This arrow means correlation length increase. These two are correlated networks. You can see that this cluster, it have more big poles. To further validate the correlation length of a generated network, we also calculate the semi-variogram to test it. To guarantee that the simulation result does not change at different realizations, a representative element volume REV should be guaranteed. To satisfy that in the highly correlated networks, the location of big pore clusters does not affect the simulation result. We calculate the absolute permeability and the breakthrough pressure in 10 realizations. From the variation, we can see that until 0.75 millimeter, the variation is acceptable, means that the smallest sample dimension need to be at least 20 times larger than the correlation length to guarantee the REV. Then in both uncorrelated and correlated networks, we did the two-phase flow simulation based on Hagen-Poisson equation and the mass balance equation. The sample is initially saturated with oil. Here the blue represents oil, and displaced by water to different saturations. After breakthrough, we solved the pressure distribution and the velocity field for two phases. Here I developed a GPU accelerator Jacobian preconditioned BRCG solver, which can solve each saturation in 1 minute. From the simulation result, we calculate the relative perm curve with an increase of spatial correlation as the cross over saturation, non-whiting phase saturation decrease. You can see here. With we choose one saturation at 0.6 to analyze the velocity field. You can see with the increase of correlation length, the preferred flow passes are obviously generated. That's the reason why the correlation lengths have more effect on the flow capability of invading phase here than the receding phase. Then we analyzed the change of stagnant saturation. With non-whiting phase saturation increase, the stagnant saturation shows non-monotonic behavior. To formalize the relation between velocity field and the stagnant saturation, we fitted this linear relation for these two elements. For the uncorrelated network, we can see that the results have a high accuracy, but for the uncorrelated ones, it has a variation near the saturation with the lowest total permeability. It may caused by the transition zone in the correlated network. At a given saturation, the ratio of flowing zones is higher in the correlated networks, but the transition zone is also more obvious here. Then we simulate the conservative solution transport in the network using the advection dispersion equation. The left part here is the concentration change of each pore unit. These two are advection section, and this one is for dispersion. This transient simulation is also paralleled by GPU node. We allocate each pore body to every kernel. This figure is the simulation result to show the stagnant saturation and the concentration distribution at the two average concentrations. For this one, the blue part represents the stagnant region and the red is flowing zone. For these two are average concentration at 0.2 and 0.6. The blue-red represent the concentration is low, and the red is the highest concentration one. This figure is 4 types of average concentration curve. This is volume averaged total concentration. With increase of the correlation length, we can see that the time needed to reach the final state is longer compared with uncorrelated one. This one is the average concentration for flowing region. It shows thickened performance for all of them. This one is for pure stagnant region. It's totally diffusion dominant. same story. For the correlated ones, it needs longer time because the cluster distribution of pores. And the last column is the flux average the concentration, the effluent at outlet. Based on the transport simulation result, we fitted the Ficken section for the effluent concentration use the Ogata-Bank equation. This equation, we can see that the dispersion coefficient shows the non-monotonic behavior. It reached the peak value at saturation of around 0.6. And for the correlated networks, the dispersion coefficient seems bigger than the uncorrelated one. Also, the mass transfer coefficient alpha between stagnant region and the flowing region is analyzed using the simulation result. From the result, we can see that alpha is slightly bigger in the correlated network and need a longer time for transfer. Finally, we proposed a semi-analytical solution to predict the mass transfer coefficient using the geometry information of stagnant regions. Because the transport simulation is usually time-consuming, especially when the saturation is low, it has a lot of stagnant parts. So here we just use the stagnant information to calculate the correct length for each stagnant cluster. And based on this geometry information, we solved this analytical solution, so we can use this analytical solution to predict the mass transfer coefficient. The conclusion have been included in the formal introduction. Summarily, the correlation length should be at least 20 times smaller than the characteristic length of porous media. The pore-scale correlation length enhance flow capability, dispersion coefficient, and also the dispersion coefficient over saturation shows non-monotonic behavior. Also, the semi-analytical solution is proposed here. It could predict the mass transfer coefficient using the information of stagnant zone. Also, as application, the low salinity water flooding is highly sensitive to the initial saturation condition. The practice of stagnant region is unfavorable for oil recovery. Also, applying the low salinity water flooding in the secondary mode seems to be more favorable. By the way, for the Interpol 2021, the abstract submission is close to deadline. Welcome to submit your abstract, especially our section. Okay, thanks for your listening.
Thank you, Senyou, for that great talk. We have a few questions coming in already. So for the audience, please, if you have any questions, just type them in the comments. So Hamed is wondering if you could please explain how to generate the correlated networks as shown in slide 5.
Sure. Slide 5. Yeah, this one. Yeah, this generation have three steps. The first step is to generate the network topology. First, we randomly generate the pore locations. Then we use the Delaunay triangle method to connect them. The H in the Delaunay triangle is the pore root, but the coordination number here we generate is very high, usually more than 10. It's not our expect. So we should decrease the coordination number. Then the second step is to generate the pore radius field. That field is correlated. Here we use the log normal one. For that field, we map the topology and the pore radius field together, and then we can allocate the radius for each pore body. So until now, we have the location, we have topology, we have the pore radius size, and also we can calculate the through radius so that we can get the network with specific correlation length. But here the sample should be big enough. If it's only have several pores or several hundred of pores, it's difficult to guarantee the correlation length because the field is random. It should be large enough to have the correlation length. Yeah.
Did you also analyze the semivariogram for real, let's say, experimentally based networks?
We didn't analyze the experimental one, but for the generated network, we use the semivariogram to validate it, to retest whether the correlation length is as our expect or not.
Okay. Yeah, it could be a nice idea to compare it also to what you get in image-based networks to see how realistic these things are. So another question we have is from Stefan Berg, who asks if you also vary the spatial wettability distribution, for example, correlated in the same way how your connectivity or how your network is correlated.
We didn't care about the wettability distribution in this work. Yeah, it's a good idea for some big pores or big pores. It may be water wetted. For some small pores, it's oil wetted. It's yeah, maybe we can do it in the late work. Yeah.
All right.
Yeah.
Caroline Dillon is asking, or is first of all complimenting you on your nice presentation. And she's also asking for the X-ray experiment, how do you maintain different saturation? Is it in situ?
I think what she talked about is this experiment. Yeah. Yeah, for this one, yeah, I think so. Yeah. For this experiment, it's a faulty experiment from a low flow rate. Yeah, you can think it's a quadratic experiment. At a low flow rate, displace it to a steady state, then inject the slot to the transport experiment. After the transport, we gradually increase the flow rate to reach another saturation. So each saturation represents a flow rate and represent a Pecklin number. Yeah, this work is led by Wahid and Shahroo. Yeah, you can find more details in our paper. Yeah.
So it's not only at residual saturation.
It's a residual saturation, but you can to some saturation we stop it and then increase the flow rate to reach another saturation. Yeah.
I see. Okay. Latif Lawal is asking how you define the pore size correlation length.
The pore size correlation length. The pore size correlation length is here is defined using the how to say the random field. The big pores close to each other. If you want to calculate the correlation length, you can, as we just said, you can use the semi-variogram to calculate this one. If the big pores close to big pores, the correlation length means it's bigger. Yeah.
All right, and then the final question. Hamid Erfani is saying, great presentation, Senyou, well done. Can you describe how to extract the semi-analytical solution parameters for a sample?
Yeah, sure. Yeah, for this one, we do the simulation first, flow simulation. Based on the velocity field, we can find the flowing region and also the stagnant region. For that stagnant region, we can have several parts. For each part, we can use the stagnant region information to calculate the characteristic length for each stagnant part. Then based on this stagnant information, we can solve this linear, this analytical solution to calculate the concentration. That means for the flowing zone, we assume the concentration is always 1 because it's very fast to reach the steady state. Then it's diffusion from the flowing zone to the stagnant region. So we can only calculate the concentration in the stagnant region. So then we can calculate the concentration and the mass transfer coefficient.
Okay, great. Thank you again, Senyou, for a great presentation. And it's also nice, such a nice discussion afterwards. So with that, we will go to our second speaker of the day, Oshri Borgman, who is a postdoc at the University of Rennes, and will be talking about the impact of matrix deformation on drying of granular materials. Oshri, the floor is yours.
Thanks, Tom. Thanks for the introduction. Thanks for the post-media team time talk for the organization. Thanks, Senyou, for the very, very nice talk that preceded me. So this work was part of my PhD, which I did at the Hebrew University of Jerusalem under supervision of Van Holtzman. And I'm now in Rennes, and he's now in Coventry University, but this work was done at the Hebrew University. And the background, or the issue that we want to discuss here is drying, and mostly in soils. We know that soils can dry and sometimes deform to certain degrees, low or high degrees of deformation. And this can lead to the creation of preferential flow paths in the soil, for example. And this example is not from, it's not due to deformation, but just to give a general picture of how preferential flow paths look in the soil. And of course, we see that this may have great effect on water flow and solid transport in the soil profile. So this is an important process and an important phenomenon that we want to investigate. And these drying and deformation processes are also relevant to other media and other processes, also industrial processes, like drying of paints and coatings of building materials, ceramics, and more. And more specifically, the question that we want to ask here is what is the relationship between deformation and drying in patterns and rates, and what is the impact of porous medium heterogeneity on these processes. So to give the general framework for the things I'm about to discuss, during the drying of soil, water is transported as liquid or vapor from the bulk liquid from the saturated region to the surface where they evaporate to the atmosphere. And this transport of water occurs through either a connected liquid pathway or through by vapor transport. And it was found that as long as liquid connectivity is maintained between the saturated region and the surface, high evaporation and high drying rates are also maintained. And another phenomenon that was described long time ago, more than 30 years ago, but this is a nice recent example from a microfluidic drying experiment, is that we can view this drying process as a sequential fluid displacement process at the pore scale. So during drying and evaporation, the pressure of the liquid in the pore decreases, and that will lead to capillary displacement, or to overcome the capillary threshold in the throat, and then air can displace the water. And when we have a sequence of these events, this is a pore-scale description of the drying process. And to introduce the phenomena of grain displacement and deformation, so this was done both experimentally and in numerical simulations for drainage, when we inject gas into a liquid saturated medium. And when the granular medium is rigid and the grains do not move, we have capillary displacement or capillary invasion of air. But in some cases, due to the very high pressure differences between the fluid phases, between the gas and the liquid, we can have a small displacement of the grains, and even small displacement of grains can modify the pore throats and the capillary invasion thresholds, and that can lead to the creation of these preferential displacement paths for the gas. So we want to take this mechanism and couple it to the drying and the evaporation process in the porous medium. And the way that we do that is by coupling a pore network model for the drying with a spring block type model for grain displacement and matrix deformation. And we start with the evaporation that reduces liquid pressure in the pores. And when the liquid pressure or the pressure difference goes beyond the critical threshold locally at the pore throat, air replaces the liquid in the pores. And that will create a temporary force imbalance on the grains close to the displacement region. And to resolve this force imbalance, the grains are slightly displaced, and this very slight displacements of grains can modify throat sizes and invasion thresholds. And this will impact the location of the next, this can impact the location of the next fluid displacement event. So in this way, we have this two-way coupling of flow and deformation, flow of the fluids and the deformation of the solid matrix. And in our simulation, we look at two basic control parameters, which were previously identified as important for these processes. One is the pore-size distribution range, lambda here. So low lambda, low pore-size distribution range, we have more homogeneous porous medium, and at high lambda, we have a more heterogeneous porous medium. And the second parameter is the initial confinement. Here I denote it as epsilon 0. The initial confinement, you can see it as the tightness of the packing of the grains. So at high confinement, the grains are tightly packed. They cannot move a lot relative to one another, so deformations are not favorable. And at low confinement, the grains are more loosely packed, and deformations or grain displacements are more favorable. So starting with some simulation results, here we start with the same initial pore-size distribution, but here we have the grains are allowed to move. So we have a deformable granular matrix, and here we have a rigid granular matrix. And we see that deformations or grain displacement can impact the drying patterns that are formed. This is the air, and this is the liquid. And we have performed these simulations over a range of parameters in pore-size variation and in initial confinement. And we generally see that preferential drying occurs more when we have low pore-size variation, so more homogeneous porous medium, and for lower confinement, so more loosely packed granular medium, we have this more preferential drying patterns. And going beyond this qualitative look, this qualitative view, we wanted to have a more quantitative results. So for that, we perform multiple simulations where we fix the parameters that define the porous medium. So for instance, here we fix the initial confinement, and we use different values for the heterogeneity. And what we can see from aggregate results from 20 simulations of each set of these parameters, we can plot the drying rate at breakthrough versus the pore-size heterogeneity, and also the same for the time for breakthrough. And we see that for low heterogeneity, we have higher drying rate at breakthrough relative to high heterogeneity, and this could be explained when we look here at these representative samples. So on this side, we have at low heterogeneity, we see a more preferential drying pattern, which at the same time maintains liquid connectivity to the surface of the sample, and thus it maintains higher drying rates. Whereas for the higher heterogeneity, we have a smaller effect of the grain displacements on the drying pattern, and the drying pattern is less preferential, and we have more drying close to the surface, and thus disconnection of the liquid pathway, which reduces the drying rates. And we also looked at this beyond the breakthrough. And so looking at the overall process, and here I plot the drying time and the saturation, the drying time versus the saturation, and the saturation versus the drying time, where here I average, again, over 20 simulations with different realizations with fixed parameters. So for low heterogeneity, we indeed see that for the duration of the process, we maintain higher drying rates, and that will lead to a faster drying or lower time to reach a certain saturation degree, as we see here. So to summarize what I've showed here, we have shown in simulations that we can capture the two-way coupling between drying and deformation in granular materials, and those grain displacements under certain conditions can promote preferential patterns in drying granular materials. And preferential drying is promoted, it can be promoted by either low pore-size heterogeneity or confining stress, or even the combination of both. And I haven't discussed a lot about the confining stress effect, but I have these results also. And preferential patterns maintain higher drying rates for longer duration of the process and reduce the drying time. And some outlook, some things that we haven't done yet and we would be happy to do, is to have an experimental validation of these modeling results, of these simulations. And another thing is that we would like to introduce some additional mechanism and simulate maybe more realistic cases, solve profiles, and to get closer to applications with this type of modeling. And with acknowledgement for some funding agencies, I conclude here. Thank you very much, and I'm glad to get your questions.
Thank you very much, Oshri, for a very lovely talk. Yeah, if you have any questions, please just write them in the comments and I'll read them out. I have a question to start off with, and I was just wondering, you know, all your numerical stuff looks like it's done in 2D, and I was wondering if the connectivity is playing like a really important role in the dynamics. Have you really looked at like the comparison between like 2D and 3D?
We haven't done simulations in 3D, so I cannot answer this directly. Of course, as you said, the connectivity will be higher in 3D. So, but I don't know how I cannot answer how the displacement of grains will impact the 3D stuff. So I don't know if, because liquid connectivity will obviously be higher in 3D, but I cannot say for sure if I expect to find also more impact of grain displacements in 3D. This is something that that I cannot say for sure. But this is something that would be really interesting to look at, of course, and to compare to 3D simulations. Maybe with other models, or maybe with developing this model.
Yeah, that would be interesting. We have a question here from Arian, and he's asking if you have looked into the effect of wettability on the process.
I tried to look at this a little bit. I haven't showed it anywhere. It was not very much developed. But the fact that with this, the type of model that we had, and this is something for for developing a modeling approach. In this type of model, the drying process was modeled as a kind of transition between steady state situations, and for that I couldn't see the effect of wettability with my model. Maybe with other models that take into effect more dynamic processes, maybe that will occur. But also we're talking about a drying process which is relatively low capillary numbers, so it's kind of a slow process, you can say. I would expect less impact of wettability, but this is something that we haven't tested directly.
Cool. We have another question from Shabina, who thanks you for your nice presentation, and then is asking, is the pore size distribution and confinement chosen in the study similar to the parameters from the naturally occurring porous media?
Yes, that's a very interesting question. So we were not able to really match between these parameters and for natural porous media, because what we wanted to look at was mostly how the range of parameters affect this phenomena, and whether this phenomena can occur at a certain range of parameters, or basically are we able to see this phenomena occurring, or are these parameters matter for drying in granular media? So I wasn't able to match this with natural parameters. But again, this is something that could be subject for further development and validation of these models, and especially with experimental validation, which I'm not familiar with much experimental work in this type of problems with drying. Let's say.
Is that something you are looking to do in the future then, or?
Hopefully, yes. I'm currently focusing on other topics, but hopefully I will be able to go back and study this more and develop this more, as I said, to a more applicative, with more applicative approach.
And may I ask, does the confining stress play a huge role in the drying process, or did you find that it was less significant than the other variables?
It's actually quite significant, I think. Just show. And it's interesting because it's what happens is that with the impact of the heterogeneity is that even if we have at small heterogeneity, even if we have very small grain displacement, they will have very large impact on the modification of the invasion thresholds, etc. So they will have a large impact on the drying process. With initial confinement, the effect is a bit different because what we have is that we just at low confinement we have large grain displacements. So it's very subtle point, but it's a bit different. And I think, and this is something that is also something that would be interesting to look in more detail, because you see this this plot here, we see like a very sharp transition between loosely confined and more tightly confined porous media, but we don't see. Sorry. Wait a minute. That we don't see, for example, here. So here we have like a more gradual decrease, whereas with the confinement we see strong effect, but in a different way. So to summarize, confinement does have a strong effect, and sometimes even stronger than changing the heterogeneity. But this effect is limited to the low confinement region, and then when we are more our grain packing is more confined, we see that the behavior is quite similar. So there's an abrupt change between low confinement and high confinement, which you don't see for the heterogeneity. So I think this is actually quite interesting point that we observed, but we haven't fully explained yet.
Okay, cool. Final question, which I guess is related, is from Constance, and they're asking, what would you expect when you place your porous system under strain?
Under strain, meaning that when it is kind of pressed together, I guess. So to me, that would increase the confinement. So granular medium under more, oh no, maybe I'm confusing strain and stress as always, but if I understand correctly, then if I interpret the question correctly, then again, I think this is what we see, that when we have higher confinement, the granular packing is more tightly packed and cannot actually move one against another, and that would act more like a rigid porous medium. And so I think the difference here between a rigid porous medium and more loosely granular porous medium is really depends on a lot on the confinement or the tightness of the granular packing. So I hope this answers the question.
Great, thank you very much. Let me just hide that. So I'd like to thank both our speakers again for some great talks. And that is actually time to conclude our session for today. So we have a great talk, another set of great talks on the 23rd of February at 3 p.m. Central European time, and they're shown here. So we recommend that you set a reminder and subscribe to our channel so that you don't forget. And with that, I would like to conclude the session and thank you all for your attendance and all for engaging with our talks. And we will see you on the 23rd of February. So thank you once again and see you soon.